Okay.
Can you give me the mouse? The pointers. Yeah. Let's now I have to hide everything.
That's good enough.
Good enough?
Yeah.
Okay. All right. Thank you for the introduction. My name is Severin Diederichs, and I will be presenting on behalf of the AdePT team our project, where we offload electromagnetic showers in G4 simulations to GPU. Full simulation must become more efficient. This very famous plot, here taken from Atlas, but it also exists for the other experiments, shows the computational needs in the progress of time versus the computing budget if there is some increase. And as you can see, aggressive R&D is needed to make it below even the optimistic budget model lines. At the same time, heterogeneous computing and computing on supercomputers has drastically changed. By now, the top 500 is really dominated by GPU clusters. And the green 500, which ranks them by energy efficiency, is completely dominated by the GPU clusters. The top 50 of the green 500 are all GPU-based. And therefore, hopefully using this energy efficiency, the idea is to use GPUs to decrease the cost of full simulation. Unfortunately, full simulation is quite expensive and a hard problem for us on the GPU. And the reason is that when we track particles in these massive detectors, we inherently have random memory access because some particles may fly in one direction while the others fly in another direction. And then you access different parts of the detector, and with that you get random memory access, which is always a problem for GPUs. At the same time, you have quite a lot of divergence in the geometry. You have simple shapes, but you also may hit complex shapes. And this increases divergence in the kernels. Additionally, you have a lot of divergence in the physics. You have a vast variety of different physics processes, which also then have different channels that they can take. So there's a lot of divergence also in the physics. Therefore, to start off, we just offload the electromagnetic particles, electron, positron, and gamma to the GPU to at least reduce the divergence in the physics. And this will additionally, it should still be very helpful because those particles are a large fraction of the cost for the simulation. So if we manage to just offload this, we can still get significant gains while avoiding the heavy divergence that would be in the physics otherwise. Okay, let's look a bit at how our project is built. According to modern standards, we rely on external libraries that are well tested and well known. And AdePT itself is really the tracking manager and takes care of the kernel scheduling and the transport of the particles on the GPU. For the physics, where we'll talk a bit more about in a second, we use G4RPM, which provides us the physics functions on the GPU and also specialized tracking on the CPU. G4RPM itself is a standalone library and used for accelerated particle transport for electrons, positrons, and gammas on the CPU alone. And we can also rely on this in AdePT. For the geometry, we use VecGeom with the GPU backend, and we use an in-memory converter from the G4 solids to VecGeom solids, or the surface model, so we can get the G4 solids, modeling the geometry on the GPU. For the magnetic field, we use a DOM and Prince integrator at the moment, and for reading field maps, we rely on the Coffee library, which is a very happy collaboration with ACTS, which is working really well for us on the GPU. Let's talk a bit more about the physics, because that's one of the core parts. AdePT relies on the G4RPM physics, as I said, but this needs a bit more of explanation. Because when G4RPM runs purely on the CPU, you would still get different results, because we do have our own custom tracking loop on the GPU. We just rely on the functions. and we use a different geometry with vector, and we have our own B field propagation. So there you can expect differences between when we run AdePT using the G4RPM physics and running pure G4RPM just on the CPU. But as you can see in this plot, here we have a simple calorimeter where you see the energy response when shooting 10 GeV electrons on it. Then you can see that the differences between G4RPM and AdePT are really small, far below the per mil level for given the statistics. So at the moment, there are a few things that we cannot do on the GPU. For example, here I said this is including the nuclear processes, which is a hadronic process which we don't model on the GPU. So we always have the fallback to G4RPM. If we have something that we cannot model on the GPU, for example, nuclear processes or fast simulation parts, which are used in Atlas for the forward calorimeter, or even some custom processes in certain regions, which we also don't have on the GPU, we just fall back to the CPU and give the particles to G4RPM. So let me explain a bit more how this full tracking structure works. In GN4, you have a stack of particles. You have a large stack, and then you just pop the first one. And if it's an electron, positron, or gamma, we give it to G4RPM to AdePT. And if it's not, we just continue the normal tracking on the CPU with GN4. If we give it to AdePT, we decide if we track it on the GPU or if we keep it on the CPU with G4RPM, and then we can interchange between the two, which is quite important, as you will see later. So AdePT itself really is this tracking on the GPU, and with that, the way we launch the kernels and the way we do the processing. So this I will now explain in quite a bit more detail. Here you see a simulation, not yet, but it will come, where you see the time running in seconds. And then here you see multiple GN4 workers doing transportation. So here, I just saw 3 GN4 worker threads, but in a real simulation, you may have as many as you have CPU cores, or twice if you go for hyperthreading, so maybe 32. And I'm just showing 3 for the simplicity of the plot. And then all of these independently pop their particles from the stack, and then they may find electrons, positrons, or gammas. So AdePT now, at the start of the presentation, will launch 2 extra threads. And these 2 extra threads are really important because what we want to do is we want to decouple the GPU from the GN4 worker threads, because we want, while the GPU is doing the electromagnetic transport, that the GN4 workers can continue with the hadronic particles or whatever else they need to do. So we don't want to block the GN4 workers when they interact with the GPU. Therefore, we have these 2 extra threads that handle this detachment. And therefore, we have these 3 buffers, which I will now explain, because as soon as the workers find any particles, they will put it to this GPU buffer, and then the thread, which is responsible for the kernel steering, will immediately offload them to the GPU. And then when you start offloading particles to the GPU, they may start their shower, and if they generate new particles, this can lead to this big shower that you can see here, where you see this typical shower profile, the tail at the end, when running the simulation with TT bar events, for example, in the big detector. And here we immediately, as soon as any particles are there, we immediately inject them on the GPU. Then after the transport or during the transport, you may want to extract some of those particles, because maybe they hit the gamma nuclear process, this we cannot handle, or they just left the GPU region, so we need to get them back. And therefore we have this from GPU buffer for the tracks. And then we asynchronously copy them back and then give them to the corresponding GN4 worker that worker can continue tracking them or whatever needs to be done on the CPU. And at the same time, we need to extract the steps that were done on the GPU. So if we hit the sensitive detector, or we want to know what's actually happening, the GN4 workers need to know what actually happened on the GPU. So we extract the steps. The steps that were done on the GPU are copied back to the workers. And again, this is done asynchronously. And for this, we have our own GPU step management thread. And this is really important because this way, the GPU can continue to work while we copy back in the background. And this is really the magic of our performance at the moment, that this asynchronous extraction. And this allows us to overlap the copying of the steps and the leaked tracks from the GPU to the CPU while doing computation on the GPU and on the CPU. And this allows us to copy back every single step without a performance impact because it's hidden. And this is really important because this allows us to really copy back everything and then call the user stepping actions and everything as before on the CPU. So we do the transport on the GPU, then we copy back to the CPU, and the CPU we call the same code as before in the code, so in the experiment frameworks. And I say without performance impact with a little asterisk here, because this is true only for real LHC setups where you have a complicated geometry and you have magnetic field where the steps are more expensive. If it's a very simple geometry where you don't have to do much, then you would see an overhead from this copy. But for what we see in the real experimental setups, this is not the case. Okay, so let's go to our target, where we actually, what we want to do is we want to port the LHC production runs to the GPU. Typically, they have a fraction of 70 to 80% for the electromagnetic physics. This leaves the rest of 20 to 30%. If we offload this, we completely hide it on the GPU, we get a theoretical speed up of 3 to 5. This is just to give you an expectations what you can expect from a realistic setup, because we will never be able to get a factor of 50 just because we don't offload the factor of 50 to the GPU. So this just sets the range what is acceptable, what you can expect for these production runs. But we need to be really fast because we are competing not with a single CPU core, but typically with the number of threads that you have, so 16 or 32 or whatever we have available. And then we have this theoretical line of speed up if we hide everything, and then we have this critical line if we are slower than this, and we would actually be slower running on the GPU. So this we really want to avoid. If we manage to really overlap everything and we are fast enough, then we cannot get faster than this. In reality, this we don't really manage because, as I said, we do the transport of the electromagnetic particles on the GPU, but we still call all the scoring and the host functions on the CPU, so we don't offload everything of electromagnetic physics, but just the transport. And this will be important when I show you the first performance plots now, because actually this theoretical speed up we can measure just by killing all electromagnetic particles immediately. So if we ignore all electromagnetic particles, we get to this red line. Looking at performance, this is an example, the HG-Cal test beam, which is the CMS test beam setup, which is used in GN4 for validation. We are shooting pions with 30 GeV, and we don't use a magnetic field. In this setup, we use the normal sensitive detector code that's available in this application, and we have a gaming GPU and a gaming CPU, but both pretty strong ones. And then here you see our strong scaling performance, where we increase the number of GN4 cores up to the maximum number of threads. We have 16 cores, so we go up to 32 threads. Then you see we are very close to the speed of light, but not exactly, as I said, because we do call the sensitive detector on the CPU. But this is a really good performance from what we can say. So we're really close to the optimal speed up. But this is not a production run. And in fact, one of the big bottlenecks typically is missing because this doesn't have a magnetic field. The magnetic field can be quite expensive because it has a lot of geometry calls. It also has divergence due to the different number of iterations, but it also has long looping tails. So for example, if some particles in the vacuum just keep looping and take quite a long time to finish, this was found a bottleneck for us. And we've resolved this bottleneck by putting these particles back to the CPU to finish it off quickly, which is faster on the CPU than on the GPU. And this gave a factor of 1.4 speed up, just this finishing of the tails. Additionally, the reading from a field map can be expensive, but we are very happy with coffee and the texture memory we are using. So for 150 megabyte field map, we only see a 10% slowdown compared to using a constant number. So using a real field map is not a big problem for us. So now we move to a little bit more challenging example where we have our own application, and it's a CMS run 3. geometry where we shoot TT bar events. And now it's a weak scaling. And now you see we still get a significant speed up, a factor of 3, which is very good. And 1.4 of this was coming from finishing on the CPU. So we managed to go from a factor of 2 to a factor of 3 by this. And then you can see that this is quite good. But now the speed of light is quite a bit further away, because if you kill everything, you would be able to get a factor of 6. So this is now getting a more challenging setup. Now we get take an even more challenging setup. That's Atlas. Now we model in full sim light. This was done in the assessment from Gian4, where we modeled the full Atlas calorimeter in full sim light using a 3D field map. And again, going up to 16 threads. Then you see that when we scale to the full machine, actually we're a bit slower on the GPU. So that's something that we really want to avoid. But this is a gaming GPU and this a gaming CPU, and the geometry is quite challenging for a vector. If we run this on a different hardware now on supercomputer on Perlmutter, on the quarter of a node, we actually see the speed up of 1.6. Comparing to G4IPM, which is an optimized, it's a 1.3. So there's still some speed up on the GPU at the moment, but it's clear that we want to improve on this. We use a quarter of the node because we have 4 GPUs on the Perlmutter node. We use a quarter of the GPUs and a quarter of the CPUs. And here, again, we scale to the maximum. But we have to say that Athena really has a different runtime, because this was just the calorimeter and not the full detector. And also in Athena, there are many optimizations to reduce electromagnetic fraction and to make it faster. And this was not used here in full sim light. So these results don't extrapolate immediately to the full production run. And therefore, it's really important, because that's what we really want to accelerate in the end, that we actually can do that. So what is missing for the production runs? This is now my personal rating of how close we are to the production. There have been many crucial developments in the last few months, but a few are still missing. So Gauss, we are relatively close. We are missing the G4 user track information, which is a custom information used by each application that they attach. And we don't have the special cuts on the process level yet. But this is something we are working on right now. For Athena, it's a bit more, because besides the G4 user track information, they also have multiple levels in the B fields, and they have current they can turn on or off. So at the moment, our B field is really just one simple map. So that's something that we need to work on. And also in the full geometry, the G4 display solid is used, which doesn't exist yet in VecGeom. So since that means we don't have it available on the GPU, therefore we cannot use it for the moment, but we will implement this very soon. CMSSW again is missing we are missing the G4 user track information in AdePT, and they also have a custom B field per volume that we also need to be able to model on the GPU. Alice, unfortunately, it's a bit further away, because they require overlap priority in the geometry. This is not supported yet by VecGeom, so there's a bit more development needed. And since this is a bit bigger, this is a bit further away for us at the moment. But we are very much in sight for these things, and we are working very hard to resolve these to hopefully get some real results very soon. And this brings me to the summary and the outlook. AdePT is a lightweight plugin to Gian4, and in principle, no changes in the user code are needed. There's only one caveat, but that might be a tricky one, that on the GPU, inherently, the tracks are processed in parallel. And so that means you have an interleaving between the tracks that you process, which may have some implications for the user code. Because in Gian4, you track everything sequentially. We offer a flexible GPU and CPU workflow, which is required to be able to turn off certain regions if need be. And our current performance results are encouraging, but in the end, only the full production runs are what is counting for the experiments. So this is what we are working very hard and with the highest priority on at the moment. The raw performance, as you've seen, must be further improved, but it's very clear that geometry is our bottleneck. And it's also clear why this can be improved, because VecGeom was really designed for vectorized CPUs and not for GPUs. So there are many things in DECGeom that we know are not optimal and that should be, we can do much better on the GPU. And therefore we have R&D ongoing for GPU optimized geometry implementations. And with that, I would like to thank all the developers and contributors to this project and open the floor for questions. Thank you. First question in the room.
If I may.
Good. Yeah,
So-
we have a couple of minutes.
So thanks a lot. Very interesting. If you can go back to slide 14, one thing that I was wondering about while just seeing this general description. So the way that you run things on the GPU seem to be very explicitly separated from what you do on the CPU thread. So is it feasible to actually run these on separate nodes even in a setup where on an HPC we have nodes with a lot of GPUs and nodes with no GPUs? Would it be possible to even develop it in the future in such a way that some of this communication happens through the network?
From my experience of HPCs, I think that it's not very feasible because the intra node, basically, if you would go from one CPU from one node to another node and then to the GPU, that's probably quite costly. We do a lot of copying back and forth, and I think that would be a problem.
Latency will be a killer.
Because, you know, the modern clusters, they do have the GPU direct links, but then you would still go from one CPU to the other CPU, which is some overhead, and then go to the other GPU. So I think also usually when you say you have a lot of GPUs on a node, I think you also have probably a lot of CPU cores on that node. And from what we see, we scale typically from for example, for Perlmutter, I think the GPU is fully loaded by the CPU cores available on that node on Perlmutter. So I don't think it would make sense to, or I don't think it's necessary to change the ratio of CPU cores to GPU cores.
Of course, my question is sort of loaded because for the high-level triggers setups of the experiments, this is being considered, that we would have a heterogeneous system. And I was wondering if that would work with this. But okay, I got my answer.
Yeah, I think you really have to simulate it and see to the end, but that would be my estimate at the moment.
We have one more question on Zoom.
Yeah, no, I just wanted to comment on the previous question. So in the experiments, both at LHC and elsewhere, we are exploring, remote usage of GPUs over the network. Not, primarily yet for simulation, but for sort of reconstruction analysis tasks. And what we find is that the latency is negligible for GPUs up to hundreds of kilometers away, as long as you do all of the calls asynchronously, much like this is doing here. So you also do the network calls asynchronously, and then you don't care because other computation is happening while transmission is happening. So I think it is possible. The question is, how do you implement it in a way that it will integrate well with the different experiment frameworks?
Also, I have to say that while we do these things asynchronously, we do have to synchronize after each step just to get the number of particles on the GPU and CPU to know how much to launch. So we do quite a lot of synchronization calls, but not for the memory copying.
Yeah, it's bi-directional communication. So it's not like you give some work to the GPU and then it's done, you don't care about it, it's written to a file or whatever. Here, you're giving work, you're getting results back, and so on and so forth. So it's a bit of a feedback loop, So that's why the latency may matter at some point.
Okay, then we should move on to the next talk. We can just stop sharing on our side. Seth, are you ready? We'll let you share.
Yeah, thank you. Hold this up. All right. Yes. Can you see the screen?
Yes.
Great. I think there might be a little bit of an echo though. Okay. Okay, thank you for the introduction earlier, Tommaso, and for the other presentation, Severin. So I'm Seth Johnson, the lead developer for Celeritas, which is computational GPU detector simulation. For further resources besides this presentation, by the way, if you look at celeritas-project.github.io, we have a full bibliography of all of our previous works and publications, presentations, and so forth. Most of this presentation is actually extracted from the recent JANT 4 review panel that we did. So I apologize if you already saw that. You've probably seen most of this already. So this is a slide that I've been showing for at least a year. The high performance computing and high energy physics intersection of the required demand for high energy physics computing power and the supply of supercomputers that's been changing. So Severin already talked to this, so we probably can skip it. But the idea is, of course, that with the LHC upgrade to high luminosity, we're going to need a lot more computational throughput. No matter what we do, we're going to need more computing, and it needs to come from somewhere. At the same time, the nature of supercomputers and computing in general and the investment in it has been changing rapidly. So not only have we gone over the past 20 years from CPU only to CPU plus GPU heterogeneous, we're now starting to see the change in investment from scientifically oriented GPUs toward sort of AI ML GPUs. And that's also going to change our capabilities over the next decade or so, I think. Those are putting more investment into reduced precision rather than for scientific computational physics applications. But either way, the availability of GPUs is going to increase because GPUs are needed for AI and ML, which are definitely the hot topic and have proven to give substantial benefits inside and outside of computational physics. So the core algorithm for being able to simulate detectors and particle transport on GPUs is basically a loop interchange. So in JANT 4, what we have is a series of events, one after the other. So these blue boxes and dots are representing a single event. And inside of event, what happens is you have a single track that's being moved through the problem. It starts by being initialized. And then that same track at every step undergoes a pre-step action, post-step action, a long step action, and additional user callbacks in the meantime. So after that step is done, you have a number of other steps. After those steps have completed, the particle dies, then you start the next track from the buffer, and then the next track, and then the next track until finally you've completed the event. With GPUs, we need to be able to do work in parallel, and because there's a dependency between one step and the next for each track, and sometimes between one track and the daughters that it spits out, what we can do is put multiple primaries in parallel because they operate independently, and then the secondaries that come off of those primaries also are independent. So instead of an outer loop over tracks and an inner loop over steps, we have an outer loop over steps and an inner loop over tracks. We have an abstraction with this red box called an action that allows us to plug in multiple GPU kernel launches one after the other so that each one operates on a bunch of tracks in parallel. And we can, at runtime, decide what physics and cross-section calculations and user callbacks and scoring and so forth we want to apply to this problem. So because, again, the kernel launch is happening inside of this action module, we can plug and play these at runtime, basically. We call each set of actions that run one after the other. So instead of a step, it's a step iteration because we're doing, 100,000 or a million tracks in parallel. So after all these step iterations are complete and the last of the tracks have been transported, that's the end of the event, and there's a synchronization point whenever we let the framework and the user code complete the end of event finalization. So this is compatible with JANT 4 and experiment frameworks. because we're still doing things within the event scope. One little caveat that's been mentioned and that we've found has been an issue for some of the detectors in particular is that there's an assumption sometimes that in a single track you have consecutive steps from that single track. So so there's example in an atlas of a muon wire detector where you look sequentially at different hits of the detector to see how close that muon passes to the wire, and it clears that minimum the next time a different track is encountered. This won't work if you're sending steps back from different tracks out of order. So the same track still does one step after the other, but it interleaves with other different tracks. So there's some gotchas for the JANT4 integration depending on how the users implemented the sensitive detector. But generally, SD code that's less stateful is more compatible, just like it was with going from single-threaded to multi-threaded JANT4. So overall, our goal in Celeritas is to accelerate scientific discovery by being a bridge between the HEP simulation world and contemporary open source scientific software development, and doing so trying to engage more students and staff in the wider scientific community, and so bringing the expertise from other fields to bear on HEP problems. So we're trying to incorporate a lot of different people from various domain expertise and improve the simulation capability for high energy physics. So most of the presentation from now is just a discussion of our recent progress. So for previous work and more descriptions of our stepping loop and the HIT algorithms, I think there's presentations back from the end of 2003 where we've discussed those. So first, some notes on the recent experiment integration progress, the benchmark demonstrations from our recent JANT4 assessment meeting, and then I'll talk a little bit about continuing development. So recently in October, we worked with the Atlas team to integrate Celeritas into the Athena framework. And out of that collaborative effort, we've really slimmed down our code and improved the capabilities and robustness of integration. So it's now only a few lines of code to integrate between Celeritas and a JANT4 application. For simpler user applications, we have a singleton that manages most of the complexity, so the user doesn't really have to do anything. For more difficult cases with frameworks that might have custom run managers like CMS, we have the ability to customize that interface so that we can have better decoupling between like the JANT4 threads and the GPU streams and so forth. There's a begin end run hook to set up and tear down the problems. We have support for JANT4 for a wide variety of versions for different ways of integration. So back to JANT4 10.5, there's certain of the user applications that still use older JANT4 versions for various physics compatibility and so forth. So we can integrate those with user actions as opposed to using the more contemporary JANT4 11.1 or 11.0 tracking manager. As a result of this work, we've done reproducibility based on the JANT4 event ID, so we can have fully reproducible results. We have integrated with the CUDA relocatable device code with downstream applications, and this is a necessity for VecGeom running that on GPU. And we have improved some other capabilities in the program. So the integration campaign was really a result of a close collaboration. So with the Atlas experts in the room, we're able to do the framework, diving into that and doing the setup for the analysis and performing that. So thanks to the people who were there for that. And from the Celeritas side, we can identify bugs or shortcomings or unexpected behaviors and add some certain features based on those. And we've been working especially with Ben and Julian after that to get these things working. So integrating with an external application is a lot more difficult than a simpler JANT4 application because they're so big. It takes 6 hours to debug and test. That was a bit of a challenge. The VecGeom toolchain has some impediments based on the way that it integrates with CUDA that we had to overcome. And then with sensitive detectors, there's a lot of what I call creative use of JANT4. So things that you wouldn't, different state changes and modifications of the particle state and side effects and so forth that you have to account for that you might not be able to if you're just doing a naive assumption that giving a hit to the sensitive detector is all you need to do. So after that October, we were able to offload to GPU and send EM tracks to Celeritas and get the hits back to the Athena for post-processing. And we've got some very good agreements for our initial comparisons, which I'll show in the next couple slides. So this is, I think, a lot of Julian's work, so thanks especially to him for this. This was a comparison of Athena simulation with and without Celeritas. So for this comparison, we disabled a couple of performance optimizations, including Russian roulette for the photons and neutrons, the frozen showers, and for this particular test, we disabled the magnetic field. We've also got only a subset of the subdetector regions enabled in this one. So this one specifically the tile calorimeters. And this problem is 10,000 events with 30 GeV pions at an eta of less than 1.7. And so as I described earlier, so this is where JANT4 is doing the hadronic physics and sends the electrons, positrons, and gammas to Celeritas on GPU, and then the hits get sent back through Athena, and all the analysis is basically done on the user side. So for this is just a cell energy deposition distribution, and we get good agreement within statistical error between the two. Same thing here. If we look at the cell position eta, good agreement, and then in phi as well. So we're pretty satisfied with our initial physics validation. We're going to be continuing to do more as we progress over time. So the JANT4 R&D evaluation gave us a set of benchmarks in conjunction with evaluation from a panel of LHC experiments and other simulation experts. So both our team and AdePT were asked to integrate our codes into these JANT4 applications. And at the end of the day, we were able to prove that we can easily integrate with these applications. We demonstrated the accuracy of our EM physics, and we demonstrated that we can achieve good performance on GPUs as well. So this is one of Makoto's favorite benchmarks, is what I've been told, is the B5 benchmark, and it includes some unusual features like parameterized replicated volumes, as well as region-dependent magnetic fields. So this required us actually to adapt Celeritas a little bit, so we added some new code. But because of our plugin oriented development process, we're able to add it without really much problem. We also had to add some features to our VecGeom, JANT4 VecGeom geometry translation engine, G4VG, which is a collaborative effort between the VecGeom and Celeritas teams. So we basically were able to use this to demonstrate the effectiveness of the code framework, and all of our detectors showed consistent results between Celeritas and JANT4. Through the model calorimeter, so these bench EM3, test EM3, we did some basic EM performance analysis in terms of accuracy, and we have accuracy within roughly the per mil level. The inaccuracy at the front here is due to the lack of statistics, but we get a good agreement for the whole of the calorimeter and energy deposition. For the CMS high granularity calorimeter, we showed that we could scale, well, first we could run effectively on just a raw CPU to GPU performance, and we showed scaling on the GPU as well. So in comparison to the AdePT, we did have some fallback or fall off in the relative speed up because we don't have yet an asynchronous kernel. And so basically our GPU is plateauing at a certain event throughput as we increase the number of CPU threads. So it's really hitting its capacity, but that capacity does show effectively a 1 CPU to 120 GPU equivalence. So the throughput that we got with a single GPU is equivalent to about the same throughput of 120 CPUs. This is also on Perlmutter, so using A100 GPU and the AMD EPYC. So finally, some ongoing work. So we're currently funded through the High Energy Physics Computational Center of Excellence coming out of Argonne, and doing some development primarily in geometry and optical physics, which are two of the main drivers for the LHC and for the other experiments in the Department of Energy. So with our analyses from the Janet 4 benchmark and going back to results that we got, a year or two ago, the bottleneck in simulation is geometry. So these are pie charts basically of the kernel times from running a single GPU, single thread, looking at the Atlas Calo only model using VecGeom1. So this was a benchmark problem from the R&D assessment that includes the calorimeter, the tile calorimeter, the barrels, and the EMEC without any sensitive detectors attached. So it's a very complex and large problem. So there's 1.8 million touchable volumes in this thing. And what we're seeing is that the raw geometry only time for this is taking about 30%. And the combination of geometry and physics, which is a combination of the field propagation and the geometry calls therein, as well as the multiple scattering and the track initialization is a combination of geometry and physics. Because these things happen within a single kernel, we can't separate the timing because of the way that CUDA works. But from our previous results, we're pretty confident that these things are dominated by the geometry calls. So out of, for example, the 29%, 22% is just doing the distance to boundary for neutral tracks. So we're seeing even more than that for the for running in the magnetic field, because it's doing multiple distance to boundary calls effectively per step per thread. On GPU, the physics is about 1% of the total runtime, and on CPU, it's about 7%. So that means that even if we're able to get to the same performance level as the CPU, and this, by the way, is CPU Celeritas, so it's running the exact same problem with VecGeom, but using the CPU kernels. That means that there's a potential speed up of a factor of 7 on GPU, and that's compared to our kind of performance parity right now that we've been seeing with this particular Athena problem, Atlas problem. So more careful analysis is needed. There's potential things that we could do to reduce the cost of charged particle propagation. The number of step counts for the neutral steps is roughly the same as in Janet 4, so we know we're doing about the same amount of work. It's just that it seems to be more expensive with the current VecGeom implementation. We're working alongside and independently, a combination of the both, with the VecGeom team for GPU optimized geometry. So the VecGeom team is doing frame surfaces, and we haven't had a chance to run this problem with that new surface-based geometry. And with Orange, we're targeting surface-based optical transport, which will work to some degree with EM problems, except that we don't have an accurate safety distance calculation yet. So that's still undergoing development. So a brief word about Orange. So this is a geometry engine that we developed at Oak Ridge 5 years or so ago for modeling nuclear engineering applications. But it's basically we adapted it to GPU and started running HEP problems on it because we needed a geometry implementation that was compatible with HIP, which is needed to run on the AMD computers, the AMD GPU cards, which are what we use at Oak Ridge. So Orange is very modular, and it's built so that all the independent pieces can be taken apart, and only a tiny bit of the code has to be modified for the tracking to surfaces. So one of the things that we've done, Elliot implemented a bounding interval hierarchy, which is kind of like a bounding volume hierarchy, which is also kind of like voxelization. But it allows us to do a tree-based search structure for navigation. So in the cases where there's hundreds especially of volumes of daughters per parent volume, this will improve the performance by factors of multiple times or more. With Julian, we're working on doing some improvements to how we evaluate the CSG tree that we're using to represent solids. We're looking at using oriented bounding boxes, so a combination of inside and outside for doing safety distance calculations. And we also have a lot of potential for simplifying the geometry and reducing the amount of work that has to be done, the amount of memory that has to be used on the GPU. The final thing is a brief note about the optical physics that we've been working on. So this is a platform portable capability. So it's meant to be run on CPU and NVIDIA hardware and AMD hardware. Unlike the approach in GEANT4, where it's the optical particles are tracked alongside the main ones, we have a totally separate tracking loop. And this is kind of the same approach that Simon Blythe's optics has. And the reason that we're doing this is because the pathology is very different for the two. You have vast number of optical photons per step, and there's very few steps per track a lot of the time. It might just be the distance going from the middle of a big volume of liquid argon to the nearest boundary, and there's no PMT there. So we are able to use the same code that's in Celeritas, so the geometry components and so forth are the same, and a lot of physics is as well. So we're designing this to scale to large clusters so that we can use MPI to integrate the results over a large number of nodes and reduce the amount of time it takes to do things like optical map generation. So things that had to be previously done with sort of a poor man's parallelism by writing stuff to different files and combining those files afterward, we're hoping to do online and improve performance even further. And our pathway to integration with GEANT4 is first by just doing direct photon emission from the Celeritas EM loop, and then having standalone application to do optical map generation. And then finally, at the end of the day, being able to do photon distributions from within GEANT4. And as kind of a proof of concept result, so we've got a sample application of a liquid argon detector that has, I don't know, 10, I think it's 10 MeV electrons. And Amanda has run this with GEANT4, with CPU using multi-threading, and with CPU track level multi-threading, and then finally on GPU. And what we're seeing is that even with just a single event on CPU, we're seeing a factor of 4 performance improvement. With scaling to the full set of CPUs, it's a factor of 75. And then on GPU, we're able to get a factor of 360. So we think we have a promising result for getting faster optical transport on GPU. So finally, we're doing a lot with the community and continuing to engage with collaborations. We've got a number of students and that we've been working with. Got 2 arriving this summer. One of them started this week. So welcome, Sal. And we are always open to working with new people and organizations. So to summarize, we've demonstrated production-ready GEANT4 integrated GP simulation. We think that we've identified the main bottleneck in terms of GPU performance, and it's really in a single place, which is GPU or geometry optimization. And we've demonstrated the things that we can do by working together across disciplines, across institutions, across nations. So thank you very much, and thanks to all the contributors and past contributors for Celeritas.
Thanks for the presentation, Seth. Okay, so yeah, we invite questions on either presentation, but starting with Celeritas. You can go ahead.
So thanks for the update, Seth. I may have asked this question before, but and this sort of goes to both of the presentations. what sort of floating point calculations do you guys use mostly? So the question is basically, do you only use double precision calculations? Do you use a mixture of single precision and double precision? If not, is there a possibility of using a mixture of single and double precision?
I can answer maybe first on the geometry side for us. So we are using mostly double precision. There are at the moment only very few occasions where you use single precision, because you have to be very careful, especially in the geometry. Otherwise, it's very easy to do errors. We do, for example, the safety is something that could be done much more in single precision, because you only have to make sure that you underestimate it and never overestimate. So at the moment, we played a little around with it. At the moment, we only use the BVH for approaching a volume. This we do in single precision, but we didn't step any further where we tried to step further, but we didn't have a safe setup yet where we really could do more mixed precision. But the goal is clearly to investigate more into going for mixed precision, because we immediately saw the gains, because mostly not even from the improved computing, but also from you read less memory. That helps a lot. And yes, there will be a workshop at CERN in July on this. Yeah, so that's from our side. Seth can add.
So from the Celeritas side, it's more or less the same thing. We're using single precision bounding boxes for acceleration. So I think really we're going to try to use reduced precision as much as we can for anything that's an acceleration, rather than for anything that requires fine grain accuracy. So I think what we could do is use coarser approximations for getting like close to a surface, but using full double precision for actual surface intersections. And for the other important thing is for when we're doing physics interactions, the momentum conservation from scattering is really important to do in double precision, because there's a square root of 1 minus x squared in there. And so if you're using single precision, you basically get 3 or 4 digits of accuracy if you're not careful. Well, if you use it at all, depending on the collision. So keeping those, yeah. So if you're using single precision for scattering, you can basically go down to per mil accuracy from the get-go. Question? Yes.
Okay, thanks.
Yeah, if I can ask some additional point, don't you worry that the next generation of GPU is designed for very low precision?
Yes, that's absolutely a concern. I mentioned that in the first motivation slide. So our understanding is that NVIDIA is attempting to develop software libraries that can compensate for that, and use the lower precision arithmetic to do higher precision arithmetic. I haven't seen that in person, but that's one of the things that they're talking about. And I think what we're going to have to do is really just minimize the places where we do have to do the double precision. So again, because geometry is our main bottleneck, I think things that can accelerate the geometry, aka using lower precision stuff to bound our surfaces, for example, will give us more opportunities to take advantage of lower precision. But yeah, so definitely a concern. But I think that overall scientific computing, outside of HEP, for example, and CFD applications and everywhere else, there's still enough demand for single and double precision arithmetic that I think they'll have to have some hardware in there. But they've definitely shifted their focus away from double precision software. So yeah, concerned.
Any other questions? Read the presentation. I think we can see hands raised if they are. I don't see any. Anything the speakers want to add?
No, I think we're fine. If there are no more questions, I hope everything was clear enough. Otherwise, you can always reach out via email and we were happy to answer more.
Well, thank you all for your time.
Thank
For
you.
inviting us.
Thanks for the update. Okay, then we can close the seminar. And stop recording.